So let's go over an example of a regression model. And here what we're going to look at is the number of linking websites to, say, some software that you want to download, and the number of downloads. So the more linking websites you have, the more downloads you have, the data are going to be positively correlated. Okay, so we have these 4 data points, not very many to test a hypothesis, and we want to first form a line. How do we do that? Linking websites is my x variable. I take the average of these guys. I have 20 plus 30, which is 50, plus 40, which is 90, plus 50, which is 140, divided by 4. The mean of x is 35. The mean of y, I have 600 plus 800, 1400, plus 1000 is 2400, plus 900 is 3300, divided by 4 is 825. So I know that 35, 825 is going to be a point on my line. Now the standard deviation, I take each data point, I subtract the mean and I square it. So I have 20 minus 35 squared, plus 30 minus 35 squared, plus 40 minus 35 squared, plus 50 minus 35 squared, or I have 225 plus 25 plus 25 plus 25, which is 500. I divide that by 3, which is 166.67. Take the square root, I get 12.9. And I do the same thing for y. I have 600 minus 825 squared, 800 minus 825 squared, 1000 minus 825 squared, 900 minus 825 squared, and add them all together, divide by 3, take the square root, 170.783. Now the correlation coefficient, I'm going to measure when x is far away from its mean is y as well, and I get a 0.83 when I do this, and these will be provided. 0.83 indicates that I have a positive relationship between x and y, and that it's fairly strong. So basically, if we're looking at the data, we have this 5900, which we would have almost a perfectly linear relationship between these if 50 weren't a little bit smaller. So we had 2600 going up by 200, 3800 going up by 200, 40,000, but then going down 100 when we go up 10. The slope, I take the correlation coefficient times the ratio of standard deviation. So I've done steps 1, 2, and 3. Step 4 is finding the slope. I take 0.83 times these ratios, and I get 11. The intercept, I know the mean of x is 35. I know the mean of y is 825. I take the mean of y minus the slope, which is 11, times the mean of x, which is 35. So I take 825. I subtract 11 times 35, which is 385, and I get 440. How do I write the line down? I write it down as y hat is equal to 440 plus 11x. Now I know the sum of errors is going to be 0. That is a point of emphasis. The sum of residuals is 0. Residuals, prediction errors, same thing. How do I find the errors? I plug in the information into a point. So how do I find the errors on these slides? Here's what I'm going to do. Let's say I want to make a prediction. The line is y hat is equal to 11 plus 440x. When x is 20, I take 20 times 11, which is 220, plus 440. My prediction is 660. The actual data is 600. So the prediction is 660. And how do I make the prediction? I have y hat is equal to 440 plus 11 times 20, which is 660. I change the 20 to 30. I have y hat is equal to 440 plus 11 times 30. I get a prediction of 770. I make a third prediction. I have y hat is equal to 440 plus 11 times 40, which is 880. And I make a fourth prediction. Y hat is equal to 440 plus 11 times 50, which is 990. The error, the data, y, minus the prediction, is the error. That's my residual. 600 minus 660, I get an error of minus 60. That's my residual. Squared error is 3600. That's minus 60 squared. So I add up all these squared errors, and I get 27,000. 27,000. That is the sum of squared errors. If we go back to calculating the standard deviation of the regression, here, that goes in this summation sign. That would be 27,000. Now I have 4 data points. I subtract 2, and I have 27,000 divided by 2, which is 13,500. My standard deviation of the regression is 116.2. What does this mean? That's how much I miss on average from my line. Okay, so I've calculated the squared errors. I have this 116.2 as my standard deviation of the regression. If we go back, that's my step 3. So if I'm testing a hypothesis, I have a test statistic. Well, I have my sample slope, which is 11. Standard deviation of the regression is 116.2. 0 is the claim. I'm claiming there's no relationship between x and y. And now I need something to measure how far apart the data are from the mean of x. How do I do that? Here is x, 20, 30, 40, 50. The mean of x is 35, so 20 minus 35 minus 15 squared is 225. Minus 5 squared, 25. 5 squared, 25. 15 squared, 225. Add them together, you get 500. Square root of 500, 22.36. That's the step 4 right here. Square root of 500 goes in that denominator. So if I'm constructing a test statistic, I have a sample slope, which I calculate. I have 0, which is my claim. I have a standard deviation of the regression, which I calculate by finding the prediction for each data point, finding the error for each data point, squaring the error for each data point, adding them up, dividing by n minus 2, taking the square root. Will this sum of squared errors be provided on an exam? Yes. Same deal for this. This is called the sum of squared deviations of x from its mean. We get a test statistic of 2.116. We're going to compare it to row 2. N minus 2 is the row we go to. We wouldn't reject. Seems a little strange. We have a pretty strong relationship. T-stat's pretty far from 0, but we just have so few data points. As you might think, this is a huge process, and maybe the computer can do it for us a little better. In Excel, we want to have x in its own column, y in its own column. Data, data analysis, regression. Note that y is the downloads, that's in cells B2 to B5. X is the linking sites, A2 to A5. If I want the residuals, I click the residuals box. If I want Excel to make a prediction for each value of x. Here's the output. Look, the residuals are here. The 11, that's my slope. Look at that test statistic calculated in Excel. Intercept is also calculated. Standard deviation of the regression is also calculated. Here's a breakdown of that regression output. The multiple r at the top is our correlation coefficient. R squared is the percentage of variation that the line explains. Standard deviation of the regression is our standard error. We're not going to worry about ANOVA in this context, although it is kind of neat. What I do want to think about is that the coefficients here represent the slope and the intercept, and this tests the hypothesis that the slope is 0.